The solutions of the differential equation dy dx equals negative ky and dy dx equals m minus ky. Suppose y prime equals negative ky, then dy dx equals negative ky, and this is separable. 1 over y dy equals negative k dx. We integrate both sides of the equation to get ln, the absolute value of y, equals negative kx plus c. Both sides of the equation to get y equals e to the negative kx times e to the c, but e to the c is a constant a, so we obtain the general solution to the differential equation. Now, if dy dx equals m minus ky, then we're going to rewrite m minus ky as negative k times minus m over k plus y. So we factor out negative k. This is negative k y minus m over k. And we let z equals y minus m over k, then dz dt equals dy dt, because the root of m over k is 0. And so y prime equals m minus ky can be rewritten as y primes equals minus kz. Remember, dy dt is y prime. But y prime equals z prime, so z prime equals negative kz. But we solved this differential equation earlier. The solution is z equals a e to the negative kt plus or minus. But z is y minus m over k, and so isolate y, we have y equals m over k equals a e to the negative kt. So every time we have a differential equation of the form dy over dt equals m minus ky, we can simply write the solution right away without having to do all of the work that we just did. The solution is y equals m over k plus a e to the negative kt. This solution can be used in mixing problems. Most mixing problems involve some solution at a certain concentration enter the container. It then thoroughly mixed with the solution inside the container already. Then it is being drained out from the container. In this class, we assume that they have the same rate in and rate out. The question is now, what is the concentration inside the container at any time t? Take alcohol, for example. If a solution contains 20% alcohol, then the concentration of alcohol is 20%. And that is, for example, for 100 gallons of the solution, 20 of the gallons are actually alcohol. Suppose a chemical in a liquid solution runs into a container holding the liquid with possibly a specified amount of the chemical already dissolved inside. The mixture is kept uniformed by stirring and flows out at the container at some known rate. We want to know the concentration of the chemical in the container at any time. And so we assume that the rate of change of the amount in the container is the rate as which the chemical arrived minus the rate as which the chemical departs. Usually, we let y be the amount of the chemical in the container at time t, and v of t is the volume of the liquid in the container at time t. Now, the volume is not the same thing as the amount of the chemical. The departure rate is therefore the rate outflowed times the concentration of the chemical over the volume in the container. So it is y of t over v of t times the outflown rate. And so the rate of change of the quantity y inside the container is dy over dt. it is the rate at which the chemical arrived minus the rate at which the chemical departs. In this case, if Y is measured in pounds, V is in volumes, and T is time, then the unit of this equation, which is a differential equation, is pounds over minute. The rate at which the chemical arrived is pounds over minute. The rate at which the outflow is also pounds over minute, but Y is the concentration, it is the amount of the chemical, the unit is pounds, V is the volume, which is gallon, and the outflow rate is gallon per minute. The mixing problems has a wide range of applications, such as in chemical reactions, discharge of pollutants into a lake, injection of a drug into the bloodstream.